Hello, this is the freshman summer video. This is on polynomials. So we kind of went over this last time, but we have this time as well. Like we're just gonna go a bit more in depth. So what are polynomials? They're just mathematical expressions. In the end of the day, they consist of variables, coefficients, and exponents. You combine these using addition, subtraction, and multiplication. And this is the form of a polynomial. Don't get too scared. This is just a general form, so don't think this is like some like really complicated thing. It's just how you write a polynomial in a broad sense. Notice if you plug in 2, you'll get a quadratic, right? Because you'll have 2, 1, and then 0. And yeah, there's an x to the 0 tacked onto this side, but you don't really need to write it because anything to the 0th power is 1. And we're not going to be covering graphing polynomials in this video. So yeah, so the big thing is Vieta's formulas, right? They come back. Vieta's formulas can also be used for any degree polynomial, actually, and think of why this makes sense. In the last video, we covered, or maybe it was 2 videos again, but we basically covered a proof for Vieta's formulas, right? We talked about why Vieta's formulas are actually true. And this is true because, it's like you're starting off in a factored form, and you're expanding, right? And we never actually made any conditions to like if the polynomial needs to be a quadratic. It just is a quadratic because it just has 2 terms. Now you can have Vieta solutions for any formula, and there's going to be a lot of problems where you'll need to know higher degree Vieta's formulas, but it'll work out where, if for example for cubic, this are the Vieta's formulas, but notice how we have this extra term, right? Your product will still be the last term. Your sum will still be the first term, right? Or just the second term. But you'll have other stuff. So for example, here you'll have your pairwise products. When you take each root, or take 2 roots at a time and multiply them and then add that stuff. That's equal to C of the A. And I'll have you prove these on your own. I don't really want to prove these right now because like they're kind of like it's kind of longer. But you can figure out why it is by yourself. So yeah, moving on. A nice problem is actually the practice problem from last time. This is the same problem from problem set 9, and you don't actually need to find the problems. This was a solution that I was mentioning. But basically what you can do, here, let me actually go into it. And so yeah, so what you can do, you can start off here, and make the polynomial, well actually first let me put the problem here. But yeah. Alright, wait 1 sec, let me go check something. Okay, sorry. Yeah, sorry. My brother just came home and oh, for some reason it paused. I don't know why my thing paused. That's annoying. I hit like a keybind or something. But yeah, so your volume, I don't know where it paused, so I'll just go off. I'll restart. But you have V is equal to A, B, C, right? V prime, your new volume is equal to A plus 2 times B plus 2 times C plus 2, right? And hopefully you can see where I'm going with this because expanding this out, you get ABC plus 2AB plus BC plus AC plus 4 times A plus B plus C plus 8, right? And how did I get that? That was kind of using symmetry. There's a lot of tricks you can do, but if you don't know those tricks, I'm not going to show the tricks. It's not the whole point of the video. But if you don't know, it's just A plus 2 times B plus 2 is just AB plus 2A plus 2B plus 4 times C plus 2. I'll just give you ABC plus 2AC plus 2AB, or no, plus 2BC plus 4C, right? And then you'll just get the same thing. So yeah. But now that we have that, we actually know all of these values. ABC, that's just equal to negative 6 over 10. The pairwise, AB plus BC plus AC, that's just equal to 29 over 10, right? That's your C over A. And then A plus B plus C is equal to, oh, I just realized I made a mistake. This is supposed to be a positive, sorry. Yeah, positive 6 over 10. For those who caught me, were probably screaming at their computer, but yeah, and then A plus B plus C is just equal to 39 over 10. All right. Now that we have that, we can plug those values in. So you have 6 over 10 plus 2 times 29 over 10 plus 39 over 10, or no, 4 times 39 over 10 plus 80 over 10, and that's equal to v prime. So if we can just do some fractions and some math, we'll find our answer. So 6 over 10 plus 2 times 29 is just 58 over 10 plus 39 is just 160 minus 4, so 156 over 10 plus 80 over 10. Let's go to v prime. What can I do to make this really easy on myself? This is just equal to 138 plus 162 over 10. And then 138 plus 162 is 300 over 10. Well, what do you know? The answer is just 30. So that's a really nice way of doing it, and I really like that way because it's so much easier to do. And you have to do, like, okay, sure, you still have to do a lot of work, but it's so much more intuitive, right? It's so much more like makes sense. And also another thing, you never have to assume if your roots are rational. With the other solution, you kind of have to use rational root theorem, but that is only working when your roots are rational. Here you have, like, you don't need to know that. Your root could be like A could be like root 302 for all you know, and it would still work, right? So yeah. All right. Okay, so moving on, we have another problem called Descartes' rule of signs. This is really niche, but it's still pretty cool. So it basically tells you a way to estimate the amount of positive roots and negative roots just by looking at the coefficients. And so what you do, you write out your coefficients, including your signs, and the number of times your sign changes is related to the number of positive roots, right? So for this one, what we have here, we have 2, -3, 1, and -6. How many sign changes? We have 1 here from positive to negative. We have 1 here from negative to positive. And we have 1 here from positive to negative. So we have 3 sign changes. So we either have 3 positive roots or 1 positive root, because it differs from an even integer all the way, and you can have -1 positive, you know what I'm saying? So it's only 3 or 1, right? And this helps because you're like, sometimes it just helps with function analyzing, or like analyzing like polynomial. So yeah, and for negative roots you just do the same thing, but you just plug in -x. So for negative roots you just have, if you plugged in -x, you'd have -2x cubed minus 3x squared minus x minus 6. There's no time where it changes from negative to positive, so you would have 0 negative roots. So I have 2 cases. Either I have all of my roots are positive, or I have 1 positive root and 1 rational root, or we're in 2 imaginary roots. I'm going to show another thing on why that's actually really helpful, but for the 1 imaginary, or for the case where you have 1 real root and 2 imaginary roots, it's helpful because now I'm not trying something that wouldn't work. So yeah. So moving on. This is just a nice practice problem. I'm not going to really go off into a different screen. So how many sign changes does it have? Well, it gives you a lot of options. It's to deal with real roots, positive roots, all that. So first thing is, okay, this looks like a Descartes rule of signs. How many times does it change roots? No, it never does. So it always stays positive. So 0 positive roots for sure. And that actually is option choice B. So that's really easy to figure out. It probably took me 15 seconds to explain, but like 2 seconds to do in my head. So it's really quick to do and it saves a lot of time. Okay, so complex roots are another important thing. And there's a lot of different theorems. You can literally fill up an entire book talking about the complex plane. There are literally entire fields of studies devoted just for complex numbers. But right now, for our purposes, we only need to know one of them, which is that if you have a polynomial where all the coefficients are real and not complex, then the non-real roots are conjugate pairs. For example, say I'm just going to whip up a random quadratic. Say you have 2x squared, or actually no, 2x cubed plus 9x squared plus 7x plus 14, right? And I'm just going to say, I don't even know if this is true. Say 2 plus I is a solution. Then the conjugate of that would also be a solution, which is just 2 minus I, right? The conjugate of a plus bi is just a minus bi. So yeah, don't get it confused the other way. But yeah, these two are going to be conjugates. Why does that make sense? This is true because when you multiply, say you have like any two conjugate pairs, right? This is just going to be 2 squared minus I squared, because difference of squares is just 4 minus I squared. But remember, I squared is just 1, or negative 1. So this is just equal to 4 plus 1, which is just a real number, right? So that's why that theorem holds true, which is pretty easy to figure out. So yeah. And I think the next one has a problem on it. Yeah, I think I'll probably take this to the whiteboard. All right, so you have this polynomial, and you know that f of 2i is equal to f of 2 plus I. And why is that important? Because that means that also f of negative 2i, because remember 0 plus 2i, the conjugate of that is a 0 minus 2i, right, is equal to f of 2 minus I, which is equal to 0. And I only have 4 solutions because it's a quartic, right? So because of that, it makes things a lot easier, because now I know that if I want a plus b plus c plus d, I just have to do x minus 2i times x plus 2i times x minus 2 plus I times x plus 2 plus I, right? Yeah, okay. Wait, did I go about that right? X minus 2 plus I, and then conjugate of that. Oh, no, sorry. This would be x minus, I knew I was doing something wrong. Okay. Alright, yeah, so that's true. So now, these first two are really easy to do. This is x squared minus 4i squared, right? Which is just x squared plus 4. Oh, actually, I don't even need to do all that. I forgot. It literally said this in the video description. There's a trick. If you want the sum, so this, right, this is the sum of coefficients, right? And this is just, like, when you plug in f of 1, that's a really quick way to find the sum of coefficients, because you're just doing 1 plus a plus b plus c plus d. So if you find f of 1 minus 1 is just equal to a plus b plus c plus d. So plugging in 1, you just have 1 minus 2i, 1 plus 2i, negative 1 plus, or negative 1 minus I, then negative 1 plus I, right? Yeah. Okay, perfect. So now you have, multiplying these two is just 1 minus 2i squared, which is 1 minus 4i squared, which is just 5. This is just 1 minus I squared, which is just 1 plus 1. So you just have 5 times 2 is equal to 10. 10 minus 1 is just equal to 9. So a plus b plus c plus d is just equal to 9. So a lot of tricks you can use, but conjugate pairs really help you. It's actually really useful because you find 2 of the roots without needing, you find a root without even needing to do any work. It's just like free. So the last one is optimization. Optimization is another pretty cool part of polynomials. You only would see this with quadratics without a calculator. With a calculator, you'll have to do this a lot with like higher degree polynomials, and not even polynomials, also like trig functions and stuff like that. But polynomials, since they're also used to represent functions from the real world, you can find that by using maxes. So polynomials have a max and min value, and for quadratic, it's like the vertex, right? And you know how to find the vertex. This is negative b over 2a. and then plugging that negative b over 2a gives you your y value. So if you were ever say, hey, find the max value of this quadratic, just do negative b over 2a, and then yeah. But another thing is also vertex form. So I'm going to also show you how to turn vertex form from standard form, right? It involves everyone's favorite thing of completing the square. So you have ax squared plus bx plus c is equal to 0. Converting that to vertex form, how do I even do that? Well, vertex form is, like I said, just completing the square. So, yeah. Yeah, okay. So you have x as your thing that you need to complete the square of. So I'm just going to divide everything by a. Or, well, actually, I can't do that because I need to make sure the quadratic stays the same. So I'm just going to pull out that a and do x squared plus b over a x. And I'm also, you guys probably know how to complete the square by now. So I'm just going to add that term that we need, right? Which is b over 2a. So it would be a times b over 2a squared. And that's plus c. Or actually, no, I would actually do minus a because we're adding on both sides and we want this to still equal to 0. So, and then I'm also adding this here. So yeah, skipping a couple intermediate steps, we just have a plus x plus b over 2a squared. And then this other stuff is honestly kind of yap, right? Like the whole point is we have our vertex in the form of just a times x plus b over 2a plus like the y naught, and that's just equal to y. You'll notice that the y is just the function definition. The only thing I really cared about showing you was this thing, because the vertex form just gives you your form of vertex is in like the form of negative b over 2a, comma, whatever that is. So I'll just say y of negative b over 2a, right? So that's just how it works. So yeah, that's pretty much the proof of why it works. So yeah, I know it's kind of like a less formal proof, but honestly, I just wanted to kind of not really gloss over it because the last time I had a proof it was like really long. So yeah, I'm trying to avoid that. But we just have one practice problem, and I'm honestly just gonna do this straight on the whiteboard or straight on the presentation. So determine the minimum value. That's just, remember, negative b over 2a. That's just equal to 12 over 4, which is equal to 3. Yeah. Okay, now what is f of 3? That is just 2 times 9 minus 12 times 3 plus 20. And that is just 18 minus 36 plus 20. And what is that? That's just 38 minus 36. And that is just equal to 2. So 2 is the minimum value of the function, and the corresponding x is x equals 3. So yeah, so that's pretty much just all the extra stuff. There's obviously a lot more stuff on polynomials, and honestly, don't take this video just like yeah, I'm done with polynomials forever. No, there's so much stuff on polynomials that definitely do your own research, because there's a lot of cool stuff that I wish I could cover. But first of all, that would make this video forever, and I don't got the voice for that. And the second thing is, honestly, like, a lot of those things you're going to learn in Algebra 2. So maybe just, like, hold off a couple months, and then you'll probably be there. So, yeah, that's pretty much it.